Our project is the law of conservation of momentum.
Shows the law of conservation of momentum. One of the most powerful laws in physics is the law of conservation of momentum. The law of momentum conservation can be stated as follows. For a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. This is the momentum lost by object 1 is equal to the momentum gained by object 2.
Related earlier ideas, John Buridan's notion of impetus is very close to the modern notion of momentum. Here's what it had to say about the matter. After leaving the arm of the thrower, the projectile would be moved by an impetus given to it by the thrower and would continue to be moved as long as the impetus remained stronger than the resistance, and would be of infinite duration were it not diminished and corrupted by contrary force resisting it or by something inclining it to a contrary motion. A good example of this would be using a pool ball and striking another pool ball, and if the first pool ball is struck hits the second one and completely stops, then all the momentum in the first pool ball is moved to the second one. If they both move at the same time, then momentum from the first one is shared through both of them.
Another example of that would be a batter who's coming up to the plate against a pitcher. The pitcher throws a 90-mile-an-hour fastball, and the batter hits the ball at 120 miles per hour. So the ball takes up what is left of the momentum of the bat. Therefore, there's a 30-plus rating of momentum. This theory, we're going to be going over to the car area. First, we have our blue car, which weighs 250 grams, which will be changing to kilograms, but this will be our starting point. We also have the red car, which is 750 grams. This is our control unit. The way this will play out is every time the blue car will be matched with the speedometer. So when the speedometer starts, we'll push the blue car into the red, hoping that it'll stick, and it will show us whether the velocity changes or not. So to set up the first one, I'll add the mass we need. Hunter over here will start our speedometer on your go.
On der 12.
There you have it. Now let's see the results. Dotted lines, but that's actually going to help us. You can see here that that was the start of the car itself. After I pushed it, it ran into the actual red car, or our control, and you can see that it starts to level out once again, and it matches that of the velocity of the first car. It's just amazing, isn't it? The way momentum works. This will be our second trial though. We'll be adding two more 500 grams, weights to the blue car. Hunter, once again, will be collecting this data for us. On 3.
1, 2, 3.
And as you can see, the blue car runs into the red car, which was stationary. And therefore, the blue car's velocity matches that of the red car's steadiness. And they both match each other's velocities through that. So we'll be... Let's set it up one more time. We're going to add 500 grams again. Set it up. All right, Hunter, let's go for it.
1, 2, 3.
Oh, sorry. Here we go. Our control being 750 grams. And our regulars, aka the blue car, we added weight to. Every time you added weight to the blue car, the velocities would decrease and the momentum would increase. Now, why is that? Well, for each time you add the 200 or the 500 grams to the car, its velocity may decrease because of how much weight it has on it, even though the momentum gained by the red car increases. So okay, I'll keep going. We have a little technical difficulties going on in the back, but when you add 500 more to this car, the velocity again decreases, but the momentum of everything increases.
Our 3 trials, we did 7 more trials. Here are our 10 trials we did for the blue car. We had 0.25 kilograms mass, and we added 0.25 each time, all the way up till we had a blue car had a mass of 2.5 kilograms. The mass of both ended up being a total of 3.25 kilograms. Each trial we found the velocity, which was given to us from our Locker Pro. And the equation to find momentum is you do mass times velocity. So we found the momentum for each mass. Here, the same way to find the momentum of both the blue and the red car, you do the mass times the velocity. This gave us the momentum of each one of the masses of the blue car and then with the red car. Okay, so on to our graph. Here on our graph, we had on the x-axis the initial momentum, and we had on our y-axis the final momentum. And we graphed the correlation between the initial momentum and the final momentum, and what we can conclude with the linear line is that initial momentum and final momentum are directly proportional. This graph represents the correlation between initial momentum and final momentum by a line graph. It shows that they're directly proportional. As one increases, the other one increases. As one decreases, they both decrease. Our drawing setup over here shows that the red car was stationary, and our blue car was one that was added weights to it each time, and the arrows show that our blue car was the one that was moving into the stationary car. This is our motion detector, and it was finding the momentum of the cars colliding with one another. From all this data we collected, we were able to find our mathematical model. Our mathematical model is the final momentum is equal to 0.9587 times the initial momentum. 0.9587 is the slope of our line up here. We got in our trials was 0.9587. The slope for a law of conservation of momentum equation is supposed to be 1. Since our slope is only off by a little bit, it shows that final momentum and initial momentum are directly proportional.
Well, I'm Hunt Diggity.
Hi, I'm Deepeg.
I'm Sarah.
Include the law of conservation of momentum. We followed it up. Hunter, what are you doing? Join us next time.